All right, General Chemistry 2 class. This is the video lecture for Wednesday, the 24th of March. And we have analysis coming up Saturday, the second part of chapter 17. So please keep that on your radar screen. Don't forget that. Keep working on it. Hopefully you were able to get caught up during spring break since it was all open pie. I'm sure that you worked on it every single day during spring break. I know I thought about working on it every day during spring break. Lab 6 is this week, the acid-base titration lab. And then worksheets 15 and 16 are going to be due this week for the online class. These are going to be due on Thursday night. We're going to walk through the process for how you would do these today. We're actually going to work through some of the very worksheet problems today. Exam 3 is coming up on April the 16th, so that's about 3 weeks away. We have a little to spare this morning. Always remember that you are unique, just like everybody else. If you can't learn to do something well, learn to enjoy doing it poorly. If it can make your job easier, it can probably make it irrelevant. It's difficult to comprehend how insane some people can be, especially when you're insane. When the going gets tough, the tough get going. The smart left a long time ago. If you think it's lonely at the top, just wait till you try the bottom. And another one. If you find yourself struggling and with motivation here, try to picture yourself suddenly unemployed, because you might be. Another good business one. And that brings us to chapter 17, acids and bases. All right. This is where we ended up. Today we're going to talk about strong acid-base titrations. And here is an example of conditions for doing titrations. You're doing a titration in lab this week. And the purpose of doing a titration, well, there are several purposes. And what I'm going to do is talk just briefly about what this means for lab. So I'm going to use this time just for a moment to talk about lab. In the beaker, in the container, in the beaker that's stirred this week in lab, you're going to be dissolving a solid acid. So this is an acid. It's like an organic acid. For example, a good one would be citric acid. Citric acid that you find in lemons, lime, citrus fruit. Citric acid has 3 hydrogens that can be titrated. So we call it a triprotic acid because H plus is also referred to as a proton. So there are solid acids, the ones we're working with, at least the ones in my labs where you're using N equals 1 hydrogen on the acid that's titrated. So you start with this acid in the beaker and the pH is relatively low because it's acidic. Now, these are all weak acids. So what happens is you find for a weak acid a typical titration curve. It's something like this. A little bit of a hook on the end here. In a titration, we can calculate the pH at every step. And for your pure enjoyment, we're going to be doing that for both strong acid, strong base, and weak acid, strong base titrations. Those are the 2 that we're really going to focus on with calculations. But from the curve perspective, what a titration tells you is how many moles of acid. It's this whole business of equivalence. If you know the moles of one thing, you can find the moles of the other. If we know the moles of base that are part of the reaction, we can know the moles of acid. And this point right here is very important because this is called the equivalence point. And so this is when the moles of hydrogen ion are equal to the moles of hydroxide ion. Or the moles of your acid are equal to the moles of base. So it's not always hydrogen and hydroxide. in an acid-base titration, which is by far the most common type of titration one does, this point is where the moles of acid are equal to moles of base. At the beginning, it's all acid. This would be milliliters of NaOH, sodium hydroxide, potassium hydroxide, milliliters of some hydroxide solution, for example. And that's what we're going to be looking at here in the strong, well, we're going to start with the strong acid, strong base calculation. But regardless, the acid, what happens is that the pH stays mostly the same. It's a slight increase because we're adding hydroxide, we're adding hydroxide, we're adding hydroxide. The pH creeps up incrementally until we get very close to the point where all of the H plus goes away. When the H plus goes away, that's this point right here. That's where the moles of hydroxide added, the moles of base are equal to the moles of the acid that we had in there. This pH is not always pH 7. Certainly it won't be for a weak acid, strong base titration. All right, so I want to come back to this. The equilibrium of water, excuse me, we know that Kw is equal to 1.00 times 10 to the minus 14th, which is equal to the hydrogen ion concentration times the hydroxide ion concentration. As we've been talking about for the last few days, if we know one of these, we know the other. And you should be able to do these calculations seamlessly. If you know hydrogen ion concentration, you can find pH, you can find pOH, you can find hydroxide concentration. You just need to know one of those things. If we take the negative log of this equation, the negative log of this number is 14.00. The negative log of 1 times 10 to the minus 14th is 14.00. And then this is equal to the negative log of hydrogen ion concentration, pH. These two multiplied, we add their exponents. Let me give you an example. Let's say we have 10 to the 2 times 10 to the 3rd. If we take the negative log of this, let's say we just take the log of this. The log of this is 2, and the log of this is 3. 10 to the 2nd times 10 to the 3rd is equal to 10 to the 5th. Because when you multiply numbers, you add their exponents. Multiply numbers, you add their exponents. You multiply numbers, you add their logs. So that's why we have the pH plus the pOH. All right, now, the other thing I wanted to mention about this equilibrium before we go any further is this. That because Kw is so tiny, 10 to the minus 14, because K is very, very small, this equilibrium lies very far to the left. What it means is that these numbers are tiny, and as we've talked about before, only 1 in 10 million molecules separates into this and this. So you've got 10 million molecules of water, only 1 hydrogen ion, 1 hydroxide. That's a fraction, a tiny fraction of the water that is in its dissociated form. What that means is this. If we have a lot of hydrogen ion, we can't have any of this, or what we have is minuscule. If we have a lot of this, we can't have much of this. So it's either or, and in an acid-base type, strong acid, strong base titration, it is either the hydroxide or the hydrogen ion that's going to be typically in excess. And that is what controls the pH. The dominant one controls the pH and the other one just follows. So how do we do these kinds of calculations? How do we find the pH of a solution that's 40 milliliters of 0.1 molar HCl before we've added any sodium hydroxide at all? Okay, so this comes back to what we ended up talking about last time with regard to the salts or the acids. Let's see, we have the strong acid, strong base, weak base. HCl is a strong acid. That means that the hydrogen ion concentration is equal to 0.1000. And I think I need a better marker. All right, so I'm taking a little bit of time for a structural component here. All right, all set. If the hydrogen ion concentration is 0.1 molar, negative log of this is 1.00. I don't even need to do this calculation because if I know the H plus concentration before I add any NaOH, it's all H plus. We have 0.1 molar hydrogen ion because it's 0.1 molar HCl, which is a strong acid, total separation. Negative log of 0.1 is 1.00. Now, I have the reaction. H2O goes to H plus and OH minus. I'm going to erase this for now because I want to use this area as a work area. Here is how we work this. We want to know the total, okay, and what we know is this, these two cannot be present together in any sizable concentration. One is typically going to dominate and control the pH. We'll talk about it. And so for 0.1 molar HCl, before we have added any sodium hydroxide, it's all HCl, the hydrogen ion dominates, the hydroxide follows. This is 0.1 molar, pH of 1. This is going to be 10 to the minus 13 molar. Like I said, minuscule. Now, in order to actually work through the problems for the titration, we need to work volume times molarity to find millimoles. I'm going to use millimoles. So here we have 40 mils, 0.1 molar HCl. Volume times molarity. Volume times molarity. If we're using liters, that gives us moles. If we're using milliliters per volume, volume times molarity gives us millimoles. 40 times 0.1 is 4.00 millimoles of H plus. Volume times molarity for H plus. When we've added 1 milliliter of hydroxide, we've added 0.1 molar NaOH, we had 1 milliliter. How many millimoles have we added? 1 milliliter times 0.1 molar is 0.1 millimoles of hydroxide. So just like in the titration lab this week, we have 4.0 millimoles of hydrogen ion in that beaker in our acid form. Now we're adding hydroxide from the burette. We've added 1 milliliter. 1 milliliter times 0.1 molar is 0.1 millimole of hydroxide. Now we have sizable amounts of both of these things in solution. Is that a happy situation? I ask you, is that a happy situation? Well, the answer is no, because when these two are present together, they just shoot over to form water. These two can't be present in any sizable amounts because they inherently form water. So what happens? It's essentially a limiting reagent problem. In other words, this reaction goes to the left until one of these things is gone. They use each other up until one of them goes to 0. And that thing that goes to 0 is hydroxide, because we didn't add very much of it. So we're left with 3.9 millimoles of hydrogen ion, 3.900 millimoles at 1 milliliter addition of NaOH. We have 3.900 millimoles of hydrogen ion in a new volume. So this is the millimoles of H plus. I'm going to erase this over here, just to give myself a little more room. Millimoles of H plus all over the total volume. The total volume of the solution, because I've added 1 milliliter of NaOH to 40 mils of hydrochloric acid. So I have 41 milliliters in my denominator, 3.900 over 41.0. This is my new molarity. This is millimoles of H plus all over milliliters, whatever, of solution. Now I calculate the molarity. Let's see. 3.9 divided by 41, 0.095, 0.2. Does it make sense? Is this number reasonable? Before I added NaOH, it was 0.1000. So yeah, something slightly less than that makes a lot of sense. Now what I do, that is the concentration. This is the molarity of H plus. So now what I do is take the negative log of it. And my pH is 1.02. 1.022. So I'm going to put the pH over here, 1.02. This is 1.00. Did the pH change much by adding 1 milliliter of sodium hydroxide to the 40 mils of 0.1 molar NaOH? No, not really. Not really. Okay. Everything I'm doing from now on, 5, 10, 20, 30, it's the exact same thing. I know that I'm starting with 4 millimoles of H plus. That is fixed. That doesn't change. What changes is the number of millimoles of hydroxide that I'm adding. So at 5 milliliters of NaOH, 5 times 0.1, 5 times 0.1 is 0.5. That's millimoles of OH. These two use each other up until one goes away. Oops, minus 0.5. This is the millimoles of H plus divided by my new volume. What's the new volume? 5 mils plus the 40 I started with. Millimoles of H plus all over milliliters solution. 3.5 divided by 45. It's 0.077777. 0.0. Just call it that. And then we do the negative log. pH is 1.109. And we keep doing this. At 10 mils, we have 1 millimole. At 20 mils, we have, let's do 20 mils, we have 2 millimoles. And we just keep on doing this right up until we get to 39.9 and then 40. So let's quickly do this with 20 mils. At 20 milliliters of NaOH, 20 times 0.1 is 2.000. That's millimoles of OH. We lose 2. These two use each other up until one goes to 0. We're left with 2. And we're left with 0. That's the way it is all the time for strong acid, strong base. This is millimoles of H plus. What's our total volume? 20 plus 40 is 60. 2 millimoles of H plus over 60 milliliters of solution. Let's see, so 2 divided by 60, 0.0333. That's the molarity of hydrogen ion at this point. And then negative log. 1.477. And that's how we find the pH at each of these steps. Let's jump over here to 39.9. At 39.9, 39.9 times 0.1 is 3.99. Right here, 39.9 milliliters of addition times 0.1 molar. This is the number of millimoles of hydroxide at this point. These two use each other up. And we're left with 0.010. That is an excess number of millimoles of hydrogen ion. Millimoles of H plus. What is our total volume? Our total volume is 40 plus 39.90, 79.90. 0.01 millimoles over 79.90. Divided by 79. Do this with me. I hope you're doing these calculations as I go along here. Do these on your calculator and check to make sure that you're doing them the same way. Or that I'm screwing up the same way you might be. Equals 0.000 1252 or 125. Now I'm going to find the pH. 3.903. 3.90. It's the excess number of millimoles of hydrogen ion over the total volume of solution. Now that we are experts at this, because we've been practicing here, folks, what do we do at 40? At 40 milliliters of NaOH, 40 milliliters times 0.1 molar is 4.000 millimoles. These two completely use each other up. They both go to 0. We don't have an excess of either one. If we don't have an excess of either one, are these both actually 0? They're very small numbers. What we do know is that they're exactly the same. And if they're exactly the same, if these two are exactly the same, if this is x and this is x, the right side is x squared, x is 1.00 times 10 to the minus 7. The pH is 7. In other words, for a strong acid, strong base titration, when we have reached equivalence, when we have the same number of moles of each one, pH is 7. And the titration curve looks like this, where this point right here is pH 7.00. How are we doing with this? I'm not hearing anything, so I'm guessing you're okay. Oops, 3.9, let me keep that. This is pH 7.0. Excuse me. Now what do we do at 41 mils? At 41 mils, it's the same thing. It's the same thing. We do the calculation the same way. Remember that now we have added 44.100. 41 mils times 0.1 molar is 4.1 millimoles. 4.1, 4.0. Now what do? We subtract 4.1 from both sides, right? No. We can't subtract more than what any one of these is. Now, instead of the hydroxide all going away, the hydrogen is the one present in smaller quantity. The hydrogen ion is now our limiting reagent, so to speak. These still go completely to the left. Now we have an excess of hydroxide. How much hydroxide? We have 0.100 millimoles of hydroxide. Remember, we're talking about 41 milliliters of addition. At 40, we had equal number of moles. At 40, At 40, that's our equivalence point. The equivalence point is the steepest part of the curve. Now we are past the steepest part of the curve. We have an excess of hydroxide ion. We know how many millimoles, and we divide by the total volume in milliliters. The total volume is 41 plus 40 to give us 81. Remember now this is hydroxide. So let's find our pH. 0.1 divided by 81. 0.00123. 0.0012345. Well, 0.0012346. 0.0012. I'll just call it 0.123. And then what I do is I find the pOH, which is 2.908. Then I find the pH, 11.092. 11.092. Okay, so here's what I want to point out. This is why titration curves look the way they do. All the way up, notice how slowly the pH changes up until we hit even 39.9. Right here. Right here. The pH is going to be 3.9. 1/10 of a milliliter later, we're at 7. 1/10, I'm sorry, 1 milliliter, and 1/10 of a milliliter later. 1 milliliter later, we're at 11. 1 milliliter later, we're all the way up here. And from now on, if we do 50, we can do this in our head now, right? 5 millimoles, we have 1 minus 4, 1 millimole of excess hydroxide. 1 millimole divided by 50 plus 40 is 90. 1 divided by 90. 1 divided by 90. 0.0111. The pOH is 1.95. And the pH is 12.046. See, once we're past, notice we've added another 9 milliliters. So way out here, our pH goes from 11.1 to 12.0. 11.1 to 12.0. About 1 pH unit for 9 milliliters of hydroxide. The big change happens right around the equivalence point. This is the usefulness of titrations. Illustrates the usefulness of titrations. So what I'm going to do here, next slide. Okay, these are the calculated values for the pHs. So compare your numbers. Notice that we've already calculated probably half of these. This is how you do calculations for strong acid, strong base titrations. This is what the curve looks like. This is the plot of the data that we just calculated. Started at pH of 1. Very slow gradual rise. We don't hit pH 2 until after 30 milliliters addition of NaOH. Then we cross that threshold. Here's the 3.9 something, or 3 point whatever it was. We calculated at 39.9 mils. And then just the other side, this would be 40. 41, and then here we have a few more data points thrown in. This is what we're looking for strong acid, strong base titration. We're looking for the steepest part of the curve. This is called the equivalence point. For a strong acid, strong base titration, no matter what it is, any strong acid, any strong base, the equivalence point will have a pH of 7. Do you remember that you learned the strong acids and you learned the strong bases? This is why. You have to be at a point where you don't even think about it. This becomes automatic. What if we started with sodium hydroxide? Let's say we start with sodium hydroxide in our beaker and now we're adding acid to that. Well, the pH of our NaOH, our pH probe sits in the solution that we're adding it to. The titrant, what's in the burette is called the titrant. What we're adding to the solution is the acid. Here our pH starts off very high because it's all basic. We're adding more and more acid, and then we have that steep curve and come down the other side. This is pretty rare. We almost always have the acid in the container and NaOH or something like NaOH. A base is our titrant. How are you doing with all this? Beautiful. All right, I'm glad to hear that. So the next step is to talk about buffer solutions. And what I'm doing in my lectures here is I'm mixing topics from chapters 17 and 18. So I'm doing some blending here. The next step is to talk about what buffer solutions are, and this will lead us to weak acid, strong base titrations. We've already talked about strong acid, strong base titrations. We're moving toward weak acid, strong base titrations. But before we do that, we have to talk about buffer solutions. In lab, buffer solutions have been mentioned. Next week in lab, it is a buffer solution lab. And we will do another round with pH, all of that beautiful stuff. So here's what a buffer is. You remember this weak acid, weak base conjugate pair business? We talked about this on Monday. Here's HCN. What's the name of HCN? Quickly, how do we name it? CN minus is cyanide. IDE ending becomes hydroic acid. Hydrocyanic acid. Hydrocyanic acid and cyanide. This is a conjugate acid-base pair where both of them are weak. This will give us a buffer solution because a buffer solution is any solution that contains a weak acid and its conjugate base together in solution. That's all a buffer is. It's not for strong, only for weak. It's a weak acid, weak base conjugate pair. This is a weak acid that's driven by Ka. This is a weak base that is driven by Ab. And we know that the Ka for this times the Kb for this is equal to Kw. That was what we covered in class in our lecture on Monday. NH4 plus, NH3, ammonium ion and ammonia. We have a weak acid, weak base conjugate pair. Remember that a conjugate pair differs by one H plus. One H plus. Would these two give us a buffer solution? If we have both of these in solution together? The answer is yes. This is HNO2, this is NO2 minus, this is nitrite. You know, this is nitrite. Nitrite is not strong, that's nitrate, it's strong. Nitrite is weak. Or nitrous acid is weak, this is nitrite. A weak acid conjugate base pair. If we have both of those species present in solution, it is a buffer. Now, these are some equations that come from the lab. Here's our Ka expression. A regular weak acid Ka expression. Ka. Hydrogen ion, anion over the weak acid itself. And remember that for weak acids, Ka is small. Ka is typically 10 to the minus 3 to 10 to the minus 12. So Ka is a relatively small number, which means most of the acid stays together as HA, and only a small fraction of it, small percentage of it associates with H plus and A minus. For a buffer solution, this and this are controlled separately. Now think of it this way. Acetic acid is a weak acid. So let's say that I take acetic acid, which is vinegar. I take vinegar, and now I add which is acetic acid. I add some acetate ion to that from, let's say, sodium acetate. We talked about salts and how to work with salts. Acetic acid and sodium acetate. These two are going to control the pH. I know this, H plus can be determined. If I take the negative log of this whole equation, the negative log of the Ka is equal to the negative log of H plus. I'm breaking this up. Remember that if we have terms that are multiplied, their logs are added. So negative log of H plus, I pull that out, and then I have this ratio of A minus to HA minus that log. pH is equal to pKa plus the log of that. So this would actually be pKa equals pH minus the log of that. If we reverse these two, we simply add the log of that. This is called the Henderson-Hasselbalch equation. Why? I don't know. I guess he just may have been the first to publish this derivation, which is pretty obvious, but nevertheless, it's called Henderson-Hasselbalch. This only is used when you have a buffer. It's used when you have a buffer because it's simple to use when you have a buffer. And we'll go through some examples of how to use this. Okay, this is where we're going to end up today. We're going to go through this list and use the Henderson-Hasselbalch equation when it's appropriate. Here we have, this is our acetic acid solution, and here's our acetate ion. And what we're going to do is we're going to start with just the acid, and then we're going to look at combinations of this and this, and then we're going to look at just this, alone in solution. Ready to go? Beautiful. Of course. All right, I'm just going to leave that equation up there because I use it all the time. All right. How do we calculate the pH right here? We have acetic acid that's 0.200 molar, and we don't have any added acetate. Well, what we have is a weak acid in water, and then it dissociates. This is a weak acid problem. We've done this. You know how to work this. This is 0.200 molar, 0, 0. Let's get rid of this. So if I plug this into the Ka expression, right? Am I given Ka? No. Let's see. Well, Ka is equal to 1.75 times 10 to the minus 5th. Some books will call this 1.8 times 10 to the minus 5th. This is equal to, at equilibrium, x squared minus 0.200 minus x. And how do we know this? We know this because we've worked a dozen problems like this already. We know that Ka at equilibrium, x squared over this. I'm not even going to do the ice table. Do the ice table if you need to, but we've done this before. And we're going to say this is equal to x squared all over like 200. Let's solve for x. X, let's see, 0.2 times 1.75 times 10 to the minus 5th is equal to x squared. Let's see, 0.2, hold on, 1.75. Enter times 0.2, and then square root. X is equal to 0.00187. Now, it's going to make a difference in that last digit. Will it make much of a difference? Not really. So, 2.73. X is equal to the hydrogen ion concentration. X is equal to the hydronium ion concentration. Negative log of that is 2.73. I'm just going to move on to the next slide and check it. 2.728. Yep, that's it. 2.728. So 2.73, I rounded from 2.728. This is how you do this calculation. It is a weak acid problem when there is no added conjugate base. Now, what do? We have a buffer at this point. And this is where it's important to recognize that this is a buffer. You don't have to use Henderson-Hasselbalch at this point, but it just makes it a lot easier if you do. We have a sizable concentration of our weak acid, and now we have a sizable concentration of our conjugate base. So pH is equal to pKa plus log of concentration in this case. All right, let me write that. I don't like to do this. CH3 COO all over CH3 COOH. This is acetate over acetic acid. This over this. This is A minus over HA. What is the pKa? Negative log of 1.75 times 10 to the minus fifth. .757. 4.757. Now, just for your information, as a general rule, this will typically have 2 decimal places instead of 3. But I'm using 3 because I'm using 3 sig figs for all of the molarities. pKa and pH are typically 2 decimal places. Typically 2 decimal places for both pH and pKa. All right, plus log of, what's this? 0.01 all over 0.200. This is a simple ratio. I don't worry about plus or minus x. If I were to put this into the Ka expression, Ka is equal to, at equilibrium. At equilibrium, I have 0.2 minus x, 0.1 plus x, and x. This is the same thing as this, believe it or not. This is simply taking the negative log of the whole thing. If you're not sure about using this, you can always use this. But for buffer solutions, it's so easy because you just take the pKa, the Ka, and they take the negative log to get to pKa. Anion concentration over cation concentration. That's it. So with this specific problem, let's calculate the pH. 0.01 over 0.2 divided by 0.2 is equal to 0.05, and the log of 0.05 is 1.3 minus 1.301. So the pH is this minus this. This ratio is less than 1. So when you take the log of it, it's going to be a negative number, minus 1.301. So let's see. Well, if we so the pH is 3.456. So the pH is 4.757 minus 1.301 to give us this. So the pH right here, so what was the pH at the beginning? Well, we've already done the calculation, whatever that was. And now the pH here is 3.456. And this is a buffer solution. Okay. How does this change as we go to this system? The concentration of acetic acid is the same. The concentration of acetate instead of 0.1 becomes 0.1. In other words, we're just changing the number here and redoing it. So 0.1 divided by 0.2 is 1/2, 0.5. Log of 0.5 is minus 0.693 or something like that, added to this. Here, the two concentrations are equal. Here, the two concentrations are equal. So this becomes 0.200 over 0.200 for this system right here. We have the same concentration of each. When we have the same concentration of each, remember what is it we have the concentrations of? It is the weak acid and its conjugate base together in solution. When they are the same, this becomes 1. The log of 1 is 0. If the log of 1 is 0, this term goes away. pH equals pKa. pH equals pKa. So the pH here is 4.757. Okay. You can do the same with this one and with this one. Notice what's happening here is that the numerator is 0.2, but then the denominator is changing, the concentration of the weak acid. The concentration of the weak acid is changing. So in other words, these numbers are going to be, this fraction will be greater than 1, and now this will be 4.757 plus the log of that number, or the log of that number is going to be a positive value. The last thing that we'll do is this. What do we do if we have a 0.200 molar acetate ion solution and none of this? None of this. This goes to 0. At this stage, we only have acetate. If we only have acetate, then we have acetate and water. Here we have the acid. Up here, it's just the acid in water. Here, it's the conjugate base in water. This is a weak base problem. Yes, of course. CH3. And this is a Kb. Describing the Kb of acetate. How do we find the Kb of acetate? Of course. This is Kw all over the Ka. Over 1.75 times 10 to the minus 5th. Kb at equilibrium is going to be x squared, this and that, all over 0.2 minus x equals x squared 0.230. We just ignore the x down here. Solve for x. This is a weak base problem. We've done these. We did this on Monday. It is the salt type of a problem. We put this in water, Kb. This is how we find the Kb. Solve for x from this specific equation. We get the hydroxide ion concentration. And from hydroxide concentration, we eventually convert to pH. Here's where we'll leave you today. These are the numbers you should get if you do these calculations. You guys see that? Let me go pull the screen down. That will help. Here we go. These are the numbers that you should get for each of these solutions. This is worksheet 16, folks. That's all it is, worksheet 16. Practice it. Use the Henderson-Hasselbalch equation. Do the calculations for worksheet 15, the strong acid, strong base titration, and then the buffer solutions. Remember that only these 5 solutions are buffers. These 5 solutions are the only ones where we have both the acid and the conjugate base together in solution. This is weak acid only. This is conjugate base only. Acetic acid, acetate ion. These 5 solutions have some of both. When we have some of both, we use the Henderson-Hasselbalch equation. You don't have to memorize it, but you probably will. All right, a little bit longer lecture today, but we had two really important concepts to talk about, and so we'll stop here.